Hello and welcome to day 4 of circles. This is properties of chords and finding segment lengths in circles. Here's the warm-up. Go ahead and do the warm-up at home. We'll go over it during class. There's a lot of vocabulary here. There's theorems and all kinds of fun stuff. So today, you're going to understand the properties of chords. By the end of class, you'll be able to find segment lengths inside circles. So our first theorem of the day says in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So what that means, ignore this bisecting arc here for a second. If we look at circle D, we can see that segment AB is 9 and segment BC is 9. So since those chords are congruent, that will tell us that the arcs that correspond to those chords are also congruent. So if arc AB is 110 degrees, then since AB and BC are congruent, arc BC will also be 110 degrees. And if arc AC is 150 degrees, we need to find arc AB. Well, arc AB is over here. I still know that arc AB and arc BC are going to be congruent because the chords that are associated with them are congruent. So I also know that arc AC plus arc AB plus arc BC is going to equal 360 degrees because that's the degree measurement of a circle. Arc AC is 150 degrees, so 150 plus the arc AB plus arc BC is going to equal 360. I know that AB and BC are the same, so I can substitute AB in and get 150 plus arc AB plus arc AB will equal 360. Arc AB plus arc AB is 2 arc ABs. If I subtract over the 150, then 2 arc ABs equals 210. Then if we divide by 2, we would see that arc AB equals 105 degrees. The next theorem, this is kind of a two-part theorem here, and we're going to show you both parts. First, if one chord is a perpendicular bisector of another chord, then the first chord is a diameter. And second is, if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So here we want to use diagram of circle E to find the length of segment AC. So we know that segment AF is 7. We could see that DB is a diameter because it goes through point E and it's perpendicular to chord AC, so it must be the perpendicular bisector. So since BD is a diameter, it bisects AC. AF has to equal FC, that's what bisector means, and they both equal 7. And 7 plus 7 is 14. So the length of segment AC would be 14. The second part of the theorem tells us that if the diameter is perpendicular to a chord, it bisects the chord and its arc. So if we look over here, we can see that BD is a diameter. It's intersecting chord CE perpendicularly. So it must be the perpendicular bisector. It also must bisect arc CE. So I could say that 9x equals 80 minus x. If I add x to both sides, I get 10x equals 80. And then dividing by 10, x equals 8. Then to find the chord measurements, 9x is going to be the same as 9 times 8, since 8 is x, which is 72. And to find arc DE, 80 minus x is going to be 80 minus 8, which is also 72. So now that I know those arc measurements, I can say that CD is 72, DE is 72, and CE would be the whole length, or 72 plus 72, which is 144 degrees. Our next theorem. In the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. Now you remember back in the past when we measure the distance from a point to a line, we have to use a perpendicular. So that's why you'll see perpendiculars here. But what we know here is in circle C, QR is equal to ST, and they're both 16 units long. We need to find the length of CU. Well, again, I know if they're congruent, they must be the same distance from the center. And since ST is 16 and QR is 16, they are congruent, so that means that CU, which is the distance from C to QR, and CV, which is the distance from C to ST, must be the same, or they're equidistant from point C. So I could say that 2x is equal to 5x minus 9. If I subtract over the 2x and add the 9, I get 9 equals 3x, and then dividing by 3, I get x equals 3. But keep in mind, it's not asking what x is. We want the length of CU, and CU equals 2x, which is 2 times 3, which is 6. Here are 3 other theorems that I'm going to briefly explain. We're going to go over them more in detail in class, but I at least want you to see them so you're aware. Our first theorem tells us if 2 chords intersect inside a circle, then the length of the 2 pieces of one chord multiplied together will equal the lengths of the 2 pieces of the other chord multiplied together. So here we can see AB and CD intersect at point E. So AE times EB is going to be equal to CE times ED. So just remember that one. Theorem number 2, if you have a chord that intersects a secant outside a circle, then what that tells us is that the outside piece, which is EC, times the full length, which is ED, is going to be equal to the tangent segment squared. And the third theorem here, if we have 2 line segments that intersect outside a circle that aren't tangents, then the outside piece times the whole thing of one is going to equal the outside piece times the whole thing of the other. So here EA times EB is going to equal EC times ED. Again, we'll do more examples of these in class. Thank you and have a great day.